Welcome back to the ICND1 series, and in this video we'll be having a look at the components that make up a switch. So first, let's start with all the external connections. Switches consist of multiple ports that either run at 10 megabits per second, 100 megabits per second, or 1000 megabits per second, and these ports are known as RJ45 ports, and they allow us to connect our end devices, our printers, our servers, our laptops to our switch. So here in the middle of the chassis, we have our RJ45 ports, which allow us to connect our devices to our switch. These ports run at these kinds of speeds, and there are loads of these ports. So normally switches come in 8 port variants, 24 port variants, or even 48 port variants. And essentially, by default, any device that we connect to our switch will have communication ability with other devices that connect to our switch. Now, also on the switch are the console ports. The console ports allow us to connect to our switch for management purposes. So allow us to connect to our switch in order to configure commands and features on our switch. Normally, the console port will be an RJ45 port, which will allow us to connect to our device via a rollover cable. On newer switches, it will be a mini USB port, which allows us to have a USB connection to our switch in order to configure the different features on our switch. Now, on the left here are what we call the status LEDs. So these LEDs, depending on the color of these LEDs, will tell us information about our switch. So as an example, it will tell us information about the different ports, what kind of speed those ports are operating at, what kind of duplex. Will tell us the status of the switch, whether the switch has a redundant power supply. So by cycling through these status LEDs, we can find out the information about our switch. So by cycling through these switch LEDs, we're able to find out information about our switch just from looking at the color codes for these LEDs. Now we can cycle through these LEDs by using the mode button. So we can see information about our switch, we can see information about power supply, about our ports by cycling through the switch LEDs by using the mode button. Now, with a switch has 4 different types of memory for specific purposes. So, switch has read-only memory. So, with ROM, read-only memory, this memory stores the bootstrap program. So, the bootstrap program is the program which is loaded during the initial boot sequence of a switch, and it handles how a switch boots. So, the bootstrap program is responsible for loading the correct files during the switch booting process. The flash memory is used to store the Cisco iOS images. All the Cisco iOS images, it's the operating system for the switch. So you can think of an iOS image as being the same as Windows 7 or Windows 10. It's an image on the switch is the operating system of the switch, which allows us to interact with the switch and allows the switch to perform features and functions and function as a switch. Now, the iOS image are stored in flash. Flash memory is a very reliable piece of memory which doesn't have any moving parts. So on our computers, on our laptops, normally our operating systems will be stored on a hard drive. The problem with a hard drive is that because a hard drive has moving parts, there's more that can go wrong with it. Now, with Cisco devices, because there's always new iOS images coming out, we're always writing and rewriting to flash memory hundreds or even thousands of times during a switch's lifespan. If we had a hard disk drive as the main storage type of memory on our devices, a lot could go wrong because we'll be continuously rewriting to the hard drive multiple times. An error could occur which would bring down our switch. So by using flash memory, it ensures that the switch is more reliable and that the switch stays up for longer. RAM, random access memory, is volatile memory, which means that any data stored in RAM is lost when the switch is powered off, and is used to store the running config. So the way the running config works is that in this case we have a connection to our switch, as we are configuring commands on our switch, those commands will be stored in the running config file, so the running configuration file. And with the running config file, if we were to power off our switch at that moment, all the commands, all the features that we've just enabled would be lost. They would be lost. So essentially, with the running config file, it stores the current running configuration of our device. As we're tapping commands, they'll be stored in the running config file. But if we were to power off our device, all those commands would be lost. Now, NVRAM stands for non-volatile RAM, is non-volatile in that anything stored in NVRAM, any data stored in NVRAM isn't lost and is retained when the switch is powered off. And the NVRAM stores a startup configuration file. So the way it works is that when a switch first boots up, it looks in the NVRAM to see if there's a startup config file, so that it knows what the initial configuration to load onto the switch. So it knows the initial configuration, all the switches that it should load onto the switch when it boots up. With the running config file, in order to save the commands we've entered and in order to save the features we've entered on a switch, we have to copy the running config file into NVRAM and into the startup config file. So then now when the switch boots up, any commands that we've configured, any features we've enabled will be retained during the boot up process and will be retained when the switch is powered off and when it starts up again. Now let's have a look into the switch LEDs. So the first LED we have on the switch is known as the system LED, and it tells us whether the switch is receiving power and whether it's functioning properly. So if the system LED is off, if there's no light next to the system LED, then it means that the switch is not receiving power. If it's amber, it means that the switch is receiving power but it's not working properly, and if it's green, it means the switch is receiving power and it's working correctly. The next LED we have is called the RPS LED, and it shows us the status of our redundant power supply that we have connected to our switch if we have one. If it's off, it means we either have no RPS or it's not being connected to the switch properly. If it's green, it means that the RPS is powered on and ready to take over for the main power supply if needed. Blinking green means that the RPS is connected but it's currently unavailable as it's powering another device. Amber means that the RPS is in standby mode or is faulty, and blinking amber means that the RPS is currently providing our switch with power because our main power supply has gone down and is faulty. Now the other switch LEDs, such as status, duplex, speed and power over Ethernet, they tell us information about our different ports on our switch. The way it works, on our switch we have different ports that allow us to connect devices to it. Each port will have a kind of like a LED light, which depending on the color of that LED, so whether it's off, whether it's green, and whether it's amber, but tells information about that port. So in this case, when we go to the stat LED, when we cycle through the stat LED, these little lights on each port will tell us the status of those ports, so whether it's up or whether it's down. Green is up, off is down. Duplex will tell us whether the port's operating in half duplex or full duplex. So if the light over here isn't green, if it's off, it means that the port's operating in half duplex. If it's green, then it means that the port's operating in full duplex. So with half duplex, either the switch or the device can send data over that cable. With full duplex, but the switch and the PC will be able to send data over that cable at the same time. The speed will tell us the speed that the port's operating at. So if it's off, it means the port's operating at 10 megabits per second. If it's green, so if this light here is green over the port, it means that the port's operating at 100 megabits per second. And if it's blinking green, it means the port's operating at 1000 megabits per second. The power over Ethernet LED tells us whether that particular port is providing power to a device over the network cable. So with some Cisco switches, they have a feature enabled which is called power over Ethernet, which means that they can actually provide power to small devices over the Ethernet cable. Normally it'll be IP phones, CCTV cameras, wireless access points, any small devices which require a small amount of power. A switch can actually provide that power to that device. If the LED on the port is off, it means that port isn't currently providing power to that device. If it's green, it means it is providing power to that device. And like I said before, it's normally used to power small devices. For example, power over Ethernet couldn't be used to power your PC or your laptop. Those require too much power. But it can be used to power devices such as IP phones, CCTV cameras, and wireless access points, the smaller devices. So now let's So now let's move into the boot process of a switch. So when a switch is first powered on, it runs a power on self-test just to check all the hardware components, to check whether all the hardware components are working, such as your CPU, your RAM, your flash memory. It's used to check whether all the ports are working and if there's any errors. If that passes, then the switch will load the bootstrap program from the read-only memory. The bootstrap program is a program responsible for loading all the correct files during the booting process. Now the bootstrap program will look in what's called the configuration register on how to boot. So the configuration register essentially tells the switch how to boot. So with the bootstrap program, it'll tell the so with the configuration register, it'll tell the bootstrap program whether the switch should boot normally and load the normal files, or whether it should boot into a special mode known as ROM mode, which is normally used when we're doing password recovery on our switch. Now if the switch is booting normally, it's going to find the iOS image in flash memory and load it into RAM. It's then going to look for the startup configuration file in NVRAM and load it into RAM. So it's a startup configuration file, just defines the initial configuration on a switch when it is loaded up. So normally a switch which has been configured with different features and functions, with different features and commands, will have a startup configuration file in NVRAM. When that's loaded, all the commands we've entered previously, all the features we have enabled will automatically be enabled on that switch. Now, if there's no startup configuration file in NVRAM, which normally occurs when we have a brand new switch, the switch will enter what's called the initial configuration dialog, essentially a guide which guides the user through setting up the basic configuration for a switch. Now, we will see this when we actually do the base configuration of a switch, but normally when the switch asks us if we want to go into initial configuration dialog, we normally enter no. We normally exit that, and then we're able to enter the commands freely by navigating the different modes of a switch. So just to add a bit more information, the configuration register will tell the switch, like for example, whether to look for an iOS image on the network on a TFTP server, whether to look for the iOS image in Flash, or whether to boot into a special mode known as ROM mode, which is normally used for password recovery. So a switch has what we call a data plane and a backplane. So two different planes on which it operates on. So the data plane refers to the actual moving of data from point A to point B. So with the data plane defines how devices that connect to a switch are able to communicate, and how traffic is moved from point A to point B. Now the speed at which traffic is moved from point A to point B depends on the speed of the interfaces. So in this case, if this interface is 1000 megabits per second, but this interface is 100 megabits per second, essentially the data plane will only be able to move data at 100 megabits per second, because this interface can only move data at 100 megabits per second. This interface can, so the way it works is this port can move data faster, but the problem is, even though we're moving data faster to this port over here, we're still limited by the speed of this port, in that we're limited by how fast data can be sent over this port to this device. So the data plane refers to the moving of data from point A to point B. Now with the backplane represents the amount of bandwidth inside the switch. And so the backplane defines how fast we can move data from one port to another port. So data plane refers how we can move data, how fast we can move data from one device to another device, and that depends on the speed of the ports. As an example, we may have really fast ports over here, but because this port over here is only limited to 100 megabits per second, in essence our data plane is only limited to 100 megabits per second. Because even though we're getting data to this port really fast, it's going to be bottlenecked, and that we're still only limited to how fast this port can send data out to this device over here. The backplane refers to the amount of bandwidth in the switch itself, and represents how fast data can be moved from one port to another port within the same switch. A switch also has what we call a switching fabric. All a switching fabric is, it's a bunch of connections between the different ports, and allows the different ports on our switch to communicate. So imagine these are the ports on our switch. All a switching fabric is, it's kind of like roads or paths between our ports, which allow those ports to be able to send data between each other and communicate with each other. Now there are different types of switching fabric, such as the bus fabric, and at the CCNA level we don't have to get into an in-depth view on what the switching fabric looks like, all we have to know that there is a switching fabric, and it's used to move data between our ports, kind of like roads or pathways that a switch can use in order to move data between the different ports. A switch also contains ASIC hardware. So ASIC hardware is hardware on a switch which is specialized for performing certain functions. So with ASIC hardware, there are two main types: port ASIC hardware and hardware ASIC. Hardware ASICs are chips on the, let's say, the motherboard of the switch, which store the forwarding tables. So with the hardware ASICs, they store the tables a switch needs in order to forward traffic. So they would tell a switch whether it should forward data and where it should forward the data to. And by having these in hardware, it makes the switch really fast at forwarding data. We also have what we call port ASICs, which are chips that reside on each port, and those chips are responsible for telling the port when to send data, when it should hold data in what's called a buffer, so so that it can wait for the switching fabric to be clear, when it should drop data, and when it should hold back data being sent out an interface if the interface is getting congested and overloaded with too much traffic. So we've reached the end of this video, and in this video we've had a look at the different components of a switch. We've looked at the 4 different types of memory: read-only memory, RAM, NVRAM, and flash. We looked at how the iOS image, the operating system of a switch, is stored in flash. Startup config is stored in NVRAM, running config is stored in RAM, and the boot app program is stored in ROM. We know that the running config is stores the commands that we're currently entering on the switch, and if at that point in time, if the switch was to go off, any commands that we have just entered on a switch will be lost. And the only time that we can save the commands we've entered and save the features we've enabled on a switch is when we copy the running config file into the startup config file. The startup configuration file is the configuration file a switch looks for during the boot up process, so that it can load the configuration onto the switch. So it's the initial configuration it looks for to load onto the switch. We've seen how the booting process works and how the switch uses the configuration register value in order to determine what files it should boot up during the boot up process and where it should look for an iOS image. And we've seen the 2 types of planes on a switch: Dataplane and a Backplane, and the switching fabric and the different types of ASICs on a switch as well. I hope this has been informative for you, and I'd like to thank you for viewing.